So here we're looking at some applications of integration here. And the first one we're going to look at is calculating the area between some curve and the x-axis. And what we looked at, when we were looking at integration in the previous unit, what we kind of learned was that if you have some function, f at x, and you're doing the integral between 2 points from a to b over x, what this represents is the area under a curve. Area under the curve. Now, what do we mean by the area under the curve? If we sketch a little graph here, we do something like this. Let's say this is our function f at x. When we say area under the curve, what we meant, if we're going from a to b, was the area essentially between this curve and this x-axis. But we also kind of said that this area that was below the curve but above the axis was sort of a positive area. And this area over here that was above the curve but below the axis was sort of a negative area. So what this kind of represents is not necessarily the, when we're talking about the area under the curve, this would kind of be the, we could say it's sort of the net area under the curve, okay? So for example, let's say we wanted to find the area between the graph of y equals x squared minus 4 on the x-axis between these 2 points, x equals -1 and x equals -3. If we were to sketch what this thing looks like, our graph is a parabola here, going like this. It's going to have intercepts of -2 and +2, and we want to integrate from -1 up to 3. So we want to go up to all the way over to here. Okay. So we want the area between the graph and the axis. So we want this area here. So if we just did our integral, okay, the integral from -1 to 3 of f at x, x squared minus 4 dx, okay, this would give us, if we call this area over here area 1, that's the part underneath the curve, underneath the x-axis, and the second part over here, a2, which is the part that is above the x-axis, doing this integral would give us the difference between a2 and a1. Okay? It would take those two areas and it would subtract it. So it's giving us the net area in that region. That's not what we really want in this question. We want the total area here and here. So basically, instead of subtracting those two areas, we want to add them together. We don't want to treat one of them as a positive area and one of them as a negative area. We want to somehow make them both positive. Okay? So this expression here is, again, the net area under the curve. Okay? Rather than the total area between the curve and the x-axis. Does this make sense? Nodding a little bit? Yeah. So I should say net area under the curve, let's say not total area between the curve and, and I'll just say x equals 0 for the x-axis. Okay? So here's sort of the problem that we have here is f at x, our function, is positive for some values of x and negative for others on this interval from a to b. Basically, it means that some point between the 2 points that we want to integrate in between, our function changes from positive to negative. So we have a positive interval and we have a negative interval, or a positive area and a negative area. What should we do in this case? Well, we should calculate their area separately and then take the absolute value, making both of them positive, and then add them together. So let's go ahead and do that for this example that we have here. We've got area 1, okay, which is our region from -1 up to +2. Okay, because +2 here is where it changes from being negative to positive. So we're going to integrate from -1, our one boundary, up to this the x-intercept basically. And what we're going to do is we're going to take the absolute value of the function on that interval. So we are going to take our antiderivative here. We'll get 1/3 x cubed minus 4x. And we're going to evaluate this integral from, oh, sorry, I'm in the wrong place here. I want from 2 to -1. So again, we're going to do the absolute value of, first we evaluate this, our antiderivative at x equals 2. So we'll get 8/3 minus 8. And from this, we are going to subtract our antiderivative evaluated at -1, which gets us -1/3 over 3 plus 4. Okay? And again, we're taking the absolute value of this entire expression. So we evaluate this, it works out to be -9. Okay? And again, we expect it to be negative because this region is underneath the x-axis. We expect it to be a negative area. So we take the absolute value of this, and we get 9 for the total area of that region. Same thing for our second area, A2. This time we're doing the integral from 2 to 3, okay, from our x-intercept up to our other limit of integration. Again, of the absolute value of our function, x² minus 4 dx. Okay? And this sort of follows pretty much the same way. We do our antiderivative, 1/3 x cubed minus 4x. We evaluate this from 2 to 3. So we're going to have the absolute value of our antiderivative evaluated at 3 minus the absolute value, absolute value of our antiderivative evaluated at 3. So that's going to be, what, 27 divided by 3. So just 9 minus 4 times 3 is 12. So evaluated at 3 minus our antiderivative evaluated at 2, which is going to give us 8 over 3 minus 8, just like it did up here. And then, again, we're going to evaluate this and take the absolute value. So if we work all this out, what we get is absolute value of 7/3, which again, because this is a region above our x-axis, we expect this to be positive. So this is just going to be 7/3. To get our total area, then, we just add these two together. 9 from our first region of integration plus 7/3 from our second region. And if we want the exact answer, this would be 34 over 3. Okay? So to sort of sum up what we're doing, what we did was we said that the area was the integral from a to b of the absolute value of our function over dx. Represents the area, let's say the total area between f at x and the x-axis. So that's the area between a curve and the x-axis. Okay? Now, occasionally you'll get a question where, as I've said here, some cases are better treated by regarding x as a function of y. So here's sort of the example. Find the area between the parabola x equals y squared and the y-axis from y equals -1 to y equals 3. So what would this situation look like? Well, if we sketch the graph, they're giving us y equals x squared. So this is kind of the inverse of y equals x squared. This would be x equals y squared. And they want us to find the area between this curve and the y-axis from y equals -1 down here up to y equals 3 up here. So basically they want us to find this area over here. Now, all of the integration that we've done up until now has been integrating with respect to x. We've been given y as a function of x, and then we have integrated with respect to x because of the way things have been set up. So here they are giving us, obviously, x equals f at y. We can calculate the area the same way as we've been doing all along, okay? Except instead of integrating with respect to x, we're going to integrate with respect to y. So our area here is going to be the integral from a to b, okay, of our function f at y. Instead of integrating over x, we're going to integrate over y. Okay? And we do this exactly the same way as we would have if we were integrating with respect to x. Okay? The process is exactly the same. Now, one thing we have to consider is if we want the area between the curve and the axis, do we need to worry about taking the absolute values in this case, like we did in the previous example? What do we think? So because all of our areas are just on one side of the y-axis, we don't have to worry about taking the absolute value. Like our function doesn't change from negative x values to, positive x values to negative x values or vice versa. So our area here is just going to be, we can just do the straight integral here. Integral from -1 to 3 of our function, y squared, integrated over dy. So we just need to take our antiderivative of y squared, which is going to be 1/3 y cubed, and we evaluate this from -1 to 3. This is going to be, let's see, if we evaluate it at 3, we get 27 divided by 3, and we're going to subtract this thing evaluated at -1, which is going to be -1/3. And this is clearly going to be 28 divided by 3. So in this case, our answer is positive, just telling us that our function exists for positive x values over this entire region of integration.